Welcome back to the channel and our comprehensive SQL series. I'm excited to take you on a journey from basic SQL to next-stage database querying techniques. In this video, we are going to cover a set of topics. From with clause to exists operator, this video has everything that you need to know about them. The with clause is one of the most underutilized yet powerful features in SQL. Think of it as creating temporary, named tables that exist only for the duration of your query. These are called common table expressions, or CTEs for short. But why would you want to do this? Imagine you're analyzing sales data and you need to find the top-performing regions, then find customers in those regions, and finally calculate some statistics. Without the with clause, you'd either write a massive, unreadable query, or you'd have to create actual temporary tables. The with clause gives you a third option: clean, readable, maintainable code. The basic syntax is beautifully simple. You start with the keyword with, followed by an alias name. Think of this as your temporary table's name. Then you use as, followed by your subquery in parentheses. After that, you can reference this alias just like any other table in your main query. Let me show you exactly how this works with practical examples. Let's start with a straightforward example that demonstrates the core concept. Suppose we have a sales table with regions and amounts, and we want to find all regions with total sales greater than $10,000. Let me break this down step by step. First, we're creating our CTE called sales_summary. Inside the parentheses, we have a completely normal select statement that groups our sales by region and calculates the total sales for each region using the sum function. Now here's the magic. Once we've defined this CTE, we can use sales_summary as if it were a real table. In our main query, we simply select everything from sales_summary and add a where condition to filter for regions with more than 10,000 in sales. This approach has several advantages. First, it's incredibly readable. Anyone can understand what's happening at each step. Second, if you need to modify the logic for calculating regional sales, you only need to change it in one place. Third, if you need to reference these regional totals multiple times in your query, you can do so without repeating the complex calculation. Now let's take this a step further. You can create multiple CTEs in a single query, and they can even reference each other. This is where the real power becomes apparent. Notice how we separate multiple CTEs with commas, not additional with keywords. Here, we first create our regional_sales CTE exactly as before. But then we create a second CTE called top_regions that actually uses the first CTE as its source. This is incredibly powerful for complex business logic. For example, you might first calculate customer lifetime values, then identify your VIP customers, then find all orders from those VIP customers, and finally calculate average order values. Each step builds on the previous one, making your logic crystal clear. Now I want to show you something truly advanced: recursive CTEs. This is where we really push the boundaries of what SQL can do. Recursive CTEs are perfect for hierarchical data like organizational charts, family trees, or any parent-child relationships. This might look intimidating, but let's break it down. A recursive CTE has two parts: the anchor and the recursive part, connected by union all. The anchor is the first select statement. We're finding all employees where manager_ID is null. These are the top-level managers, the CEOs. We give them level 1. The recursive part is the second select. Here's where the magic happens. We're joining the employees table with our own CTE. We're saying find all employees whose manager is someone we've already found, and give them a level that's one higher than their manager's level. SQL will keep running this recursive part until it can't find any more matches. The result is a complete organizational hierarchy showing every employee and their level in the company structure. This technique can solve problems that would be incredibly difficult or impossible with traditional SQL. The last one to look at is the CTE with window functions. This SQL query effectively retrieves the top 5 most expensive products by utilizing a common table expression, CTE, named ranked_products in conjunction with a window function. Within the CTE, row_number is applied over the products table, ordering the rows by price in descending order. This assigns a unique rank to each product, with the highest priced product receiving a rank of 1. Finally, the main query then selects all columns from this ranked_product CTE, filtering the results to include only those products where the assigned rank is 5 or less, thereby isolating the 5 most expensive items. Now let's move on to our second major topic, the fetch clause. If you've ever built a web application or mobile app, you've definitely dealt with pagination. You know, showing 10 results per page, with next and previous buttons. The fetch clause is SQL's elegant solution for this common requirement. But fetch isn't just about pagination. It's about precision control over your result sets. Maybe you want the top 5 products by price, or the first 25% of your customers by registration date. Fetch gives you this control with clean, readable syntax. The basic syntax follows a logical pattern. You order your results first, because you need to define what first means, then you use offset to skip some rows if needed, and finally fetch to specify exactly how many rows you want. Let's see this in action with a simple example. This query is asking for the 3 highest paid employees. We order by salary in descending order, so the highest salaries come first, then we fetch first 3 rows only. The beauty of this syntax is how readable it is. Anyone can understand exactly what this query does, even if they are not SQL experts. Next, we're implementing pagination. Offset 5 rows means skip the first 5 rows. Then fetch next 10 rows only means give me the next 10 rows after those we skipped. So if you think of your results as pages of 10 items each, this query would give you page 1, after skipping page 0. For page 2, you'd use offset 15 rows. For page 3, offset 25 rows, and so on. The fetch clause has some advanced features that can be incredibly useful in specific scenarios. Let me show you 2 important ones. Instead of specifying an exact number of rows, you can specify a percentage. This query gives you the oldest 25% of your customers by registration date. This is particularly useful when your table size varies significantly over time. Here's another powerful feature. The with ties clause is brilliant for handling edge cases. Let's say you want the top 5 students by score, but what happens if the 5th and 6th students have exactly the same score? With ties ensures you get all students with the 5th place score, even if that means returning 6 or 7 rows instead of exactly 5. This is crucial for fairness in many business scenarios. Imagine you're selecting top performers for bonuses. You wouldn't want to arbitrarily exclude someone just because they happen to be sorted after someone else with the identical performance score. Here in this query example, you can better understand the implementation of the pagination as explained previously. This example illustrates how to implement pagination in SQL, allowing for the retrieval of data in manageable chunks, often referred to as pages. For page 1, the query retrieves the initial 10 records from the orders table, sorted by order_date, effectively fetching the very first set of data without skipping any rows. To retrieve page 2, the subsequent 10 records, the query first offsets, or skips, the initial 10 rows that constituted page 1, and then fetches the next 10 rows only, thereby providing the next sequential set of data for the second page. Let's start with arithmetic operators. You might think, it's just basic math. right? But in the database world, arithmetic operations become incredibly powerful for business intelligence, financial calculations, and data transformation. SQL provides 5 basic arithmetic operators: addition, subtraction, multiplication, division, and modulo. But the real magic happens when you combine these with your data to solve real business problems. Here's a practical example that demonstrates multiple concepts. This simple query transforms raw inventory data into business intelligence. We're not just looking at individual prices and quantities, we're calculating the total value of each product line. This is fundamental for inventory valuation, insurance calculations, or identifying your most valuable stock. But let's take this further with a more complex business scenario. Now we're doing real business analysis. We calculate absolute profit by subtracting cost from selling price. But more importantly, we calculate profit percentage using the formula profit divided by cost price multiplied by 100. This percentage is crucial for understanding which products are most profitable, not just which ones generate the most absolute profit. This query demonstrates the use of the modulo operator. We're selecting the order ID and the total amount from the orders table. The key part here is total_amount %10 as remainder. The modulo operator, represented by the % sign, calculates the remainder after dividing total_amount by 10. This can be useful for various tasks, such as distributing records evenly or checking for divisibility. Moving on to complex calculations, this second query shows how to derive meaningful metrics from existing data. We're retrieving the product name, cost price, and selling price from the products table. Beyond that, we calculate 2 new fields: profit, which is simply selling_price, cost_price, and profit_percentage. The profit_percentage is derived by dividing the profit by the cost price and then multiplying by 100, giving us the profit as a percentage of the cost. This illustrates how SQL can perform powerful inquiry analytics. This section demonstrates data arithmetic, a powerful feature for calculating time differences directly within your SQL queries. Here, we're selecting the order_date and delivery_date from the orders table. Crucially, we then calculate delivery_date, order_date, and alias it as days_to_deliver. This operation directly yields the number of days between the order and delivery, making it straightforward to analyze fulfillment times. Next, we look at conditional arithmetic, which allows you to apply different calculations based on specific conditions, often using a case statement. In this example, we're selecting employee_name and base_salary from the employees table. The case statement then calculates an adjusted_salary. If the department is sales, the base_salary is increased by 15%. If it's IT, it's increased by 10%. Otherwise, the base_salary remains unchanged. This is a highly flexible way to implement business logic directly in your queries. Wildcard operators are special characters that represent other characters in search patterns. Think of them as placeholders that can match different types of text. SQL provides several wildcards, but we'll focus on the most important and widely supported ones. The % is the most versatile wildcard. It matches 0 or more characters of any type. Let me show you how powerful this is. This finds all customers whose names start with A. The % symbol says match any characters that come after A. It could be 1 character, 10 characters, or no additional characters at all. The next one finds names ending with son like Johnson, Anderson, Peterson, and so on. The % at the beginning matches anything that comes before son. This finds names containing and anywhere within them like Anderson, Alexander, Miranda, or any name with and in it. The underscore is more precise. it matches exactly one character. This finds product codes that are exactly 4 characters long. Each underscore represents exactly one character, so this pattern requires exactly 4 characters, no more, no less. Next query finds names where the second character is A, like James, Sarah, or David. The first underscore matches exactly one character, A matches the literal A, and % matches anything after that. The last one looks out for a specific pattern at a specific position like EA001 or UI001. Now, let's look at square brackets, which are used to define a character range or a set of specific characters for matching. For instance, if you want to find names that start with A, B, or C, you would write this query. Here, square bracket ABC will match any single character that is either A, B, or C, followed by any sequence of characters due to the % sign. Similarly, to match names starting with letters A through F, you can specify a range like this. This will match any single character from A to F, followed by anything else. And finally, for numerical patterns, you can use ranges as well. To find phone numbers starting with 2, 3, or 4, you'd use the last query. This efficiently filters for records where the first digit of the phone number falls within that specified range. Next, we have the caret symbol within square brackets, which signifies not in range, or not one of these characters. This is incredibly useful for excluding specific patterns. For example, if you need to find customer names that do not start with the letters A, B, or C, you would use this wildcard. Similarly, to identify product codes that do not begin with a number, you can apply the caret symbol within the brackets to exclude the numerical range from 0 to 9. Finally, wildcards become even more powerful when you combine them to create highly specific search patterns. To illustrate, if you want to find all email addresses that are from Gmail, you would combine the % symbol to match any characters before and after the fixed string at Gmail, followed by another % symbol to match the domain extension. Another common use case is when looking for product codes that follow a very specific structure. For instance, you could search for codes that start with PR, followed by an underscore, and then 2 specific digits, allowing for any characters afterwards. This demonstrates how combining wildcards enables precise pattern matching for complex data. The update statement in SQL is used to modify existing data within your database tables. Its core purpose is to change values in one or more columns for rows that meet a specified condition. The basic syntax begins with the update keyword followed by the table underscore name you wish to modify. Then, the set clause specifies which column to update and its new value. You can update multiple columns by separating them with commas. Crucially, the where clause is used to define the condition that determines which specific rows will be updated. Without a where clause, the update statement would modify every single row in the table. Starting with a simple use case, a single column update allows you to change the value of just one column for a specific record. For example, to adjust an employee's salary, you would specify the employees table, set the salary to a new value, and use a where clause to target the exact employee underscore ID you want to modify. When you need to modify several pieces of information for a particular record, you can perform a multiple columns update. Here, for a given customer, you might update their email address, phone number, and city simultaneously by listing each column and its new value in the set clause, separated by commas, all linked to a specific customer underscore ID. Conditional updates allow you to apply changes to a group of records that meet certain criteria. For instance, to increase the price of all products within a specific category, like electronics, you would update the products table, set the price to its current value multiplied by a factor, and apply a where clause based on the product category. Updates can also incorporate calculations, enabling dynamic adjustments to data. An example of this is giving a salary raise to employees based on their department and experience. You would set the salary to its current value plus a calculated percentage increase, but only for employees in the sales department who have more than 5 years of experience. An update with a subquery is useful when the rows to be updated depend on data from another table or a complex condition. For example, to mark orders as shipped that have corresponding entries in a shipments table for the current date, you would update the orders table and use the IN operator with a subquery to select the relevant order_IDs from the shipments table. Updating with a join allows you to modify data in one table based on related information in another. Consider giving a bonus to employees in a specific department. You would update the employees table, set their salary by a certain percentage, and join it with the departments table on their respective department IDs, then filter for a specific dept_name like IT. Finally, an update using a case statement provides highly flexible conditional logic for setting values. This is ideal when the update value depends on multiple conditions. For instance, to calculate bonuses for employees based on their performance_rating, you would set the bonus column using a case statement. This allows you to assign different bonus percentages based on whether the rating is excellent, good, average, or any other performance level, providing a default value if none of the conditions are met. The alter table statement in SQL is specifically designed to modify the structure of an existing table. This is distinct from changing the data within the table. Instead, it's about changing the table's definition itself, such as adding new columns, removing old ones, or modifying column properties. First, to add a column, you use alter table followed by add column. You can add a single column, specifying its name and data type, like adding a phone column to the employees table. For adding multiple columns simultaneously, you list each new column with its data type, and you can even define a default value for them, such as adding created_date and status to the customers table, with status defaulting to active. Conversely, to remove a column from a table, you use drop column. This is also straightforward. Alter table followed by drop column and the name of the column you wish to remove, for example, dropping the phone column from employees. Similar to adding, you can drop multiple columns by listing each drop column clause sequentially. Modifying a column's data type allows you to change how data is stored in that column. For instance, you might alter column to change an employee's salary from an integer to a more precise decimal type. You can also use this to add or change column constraints, such as ensuring a price column in the products table can no longer be null by setting it not null. Renaming a column is simple with alter table and rename column. You specify the original column name and then use to followed by the new column name, such as changing emp_name to employee_name in the employees table. If data model changes or requirements evolve, you might need to remove existing constraints. You can drop constraint by specifying its name. For example, removing a check_salary check constraint from the employees table. Similarly, a foreign key can be dropped by its name if the relationship is no longer needed. You can also rename an entire table using alter table. You simply specify the old_table_name and then use rename to followed by the new_table_name to reflect organizational or naming convention changes within your database. Finally, adding constraints is crucial for maintaining data integrity. You can add constraint to define a primary key, ensuring unique and non-null identification for records, like employee_ID. You can also add a foreign key to enforce referential integrity between tables, such as linking orders to customers via customer_ID. Check constraints ensure data meets specific conditions, like a salary being greater than 0. Lastly, a unique constraint guarantees all values in a column, such as email, are unique. The like clause in SQL is used for pattern matching within where clauses, allowing you to search for data that partially matches a specified string rather than requiring an exact match. This is particularly useful when you're looking for values that contain, start with, or end with certain characters. The basic syntax involves using select to retrieve data, followed by a where clause where you specify the column you want to search and then the like keyword, followed by the pattern you're looking for, enclosed in single quotes. To find data that begins with a particular sequence of characters, you use the % symbol after your desired prefix. For instance, if you want to find all customer names that start with John, you would use the pattern John followed by a % symbol. Similarly, to find all cities starting with new, you would apply new followed by the % symbol. Conversely, to search for data that ends with a specific sequence, you place the % symbol before your desired suffix. For example, to retrieve all email addresses ending with .com, you would use a % symbol before .com. This also applies to finding documents where the file name ends with .pdf. When you need to find data that contains a specific sequence of characters anywhere within the string, you use the % symbol both before and after your pattern. So, to find customer names that contain Smith anywhere in them, you'd enclose Smith between two % symbols. This is also how you would search for descriptions that contain the word urgent. The underscore wildcard allows you to match a single character, which is useful for defining patterns of exact length or character position. To find product codes that are exactly 5 characters long, you would use 5 consecutive underscores. Or, if you wanted to find customer names where the second character is a, you'd use an underscore for the first character, followed by a, and then a % symbol for any characters thereafter. The not-like operator is used to exclude patterns. It retrieves records that do not match the specified pattern. For instance, to find customer names that do not start with the letter A, you would use not-like a%. Similarly, to list all email addresses that are not from Gmail, you would use not-like with the pattern % at gmail.%. By default, like searches are often case-sensitive, depending on your database. To perform a case-insensitive search, a common approach is to convert both the column data and your search pattern to either upper or lower case before applying like. Some databases, like PostgreSQL, offer a dedicated like operator for direct case-insensitive pattern matching, making the syntax simpler. Finally, you can combine wildcards to create more complex and precise patterns. For example, to find phone numbers that strictly follow a digit format, you'd use underscores and hyphens. Another instance is matching product codes that start with PR followed by exactly 3 digits, achieved by combining literal characters with multiple single-character underscore wildcards. The between and in operators are powerful tools in SQL used to filter data efficiently. The between operator is designed to select values within a specified range, while the in operator allows you to specify multiple possible values for a column, acting as a concise alternative to multiple OR conditions. When working with numerical data, between is excellent for defining a range. For instance, to retrieve employees whose salary falls between 50,000 and 80,000, you would use between 50,000 and 80,000. Similarly, you can filter customers by an age range, such as those between 25 and 35. The between operator is also highly effective for filtering data based on date ranges. To find all orders placed within the year 2024, you would specify the order underscore date as between the first day of January 2024 and the last day of December 2024. You can also use dynamic date calculations, like finding events happening within the next 30 days from the current underscore date. If you need to exclude a specific range, you use the not between operator. For example, To find employees whose salary does not fall between $30,000 and $60,000, you would use not between with that salary range, effectively selecting salaries outside of that specified boundary. The IN operator simplifies queries when you want to match a column against a list of specific values. Instead of writing multiple or conditions, you can simply list the desired numerical values within parentheses. This is useful for selecting employees belonging to specific department IDs like 1, 3, 5, or 7, or for filtering specific product IDs. Similarly, the IN operator works perfectly with string values. To retrieve customers residing in New York, Los Angeles, or Chicago, you would list these city names within the IN clause. This also applies to filtering orders by specific status values such as pending, processing, or shipped. When you want to exclude records based on a list of specific values, the not IN operator is your go-to. For instance, to find employees who are not in the HR or finance departments, you would use not IN with that list of department names. This also applies to excluding sales data from particular regions like North or South. A powerful application of the IN operator is combining it with subqueries. This allows you to filter data based on results from another query. For example, you can find all employees who belong to departments with a budget greater than $100,000 by using a subquery to first select the dept_IDs from the departments table that meet that budget criteria, and then checking if the employee's department_ID is in that resulting set. Similarly, you can find products that were ordered today by using a subquery to get product IDs from order_items for the current date. Finally, you can combine between and IN for more complex filtering needs. For example, to find employees whose salary falls within a certain range, say $40,000 and $70,000, and who also belong to specific departments like IT, sales, or marketing, you can link both conditions using the IN operator, providing highly precise data retrieval. The case statement in SQL is a powerful construct that allows you to implement conditional logic directly within your queries. It's essentially SQL's way of performing if-then-else operations, enabling you to return different results based on various conditions. The basic syntax starts with the case keyword. You then define one or more when clauses, each with a condition and a result to be returned if that condition is true. An optional else clause provides a default result if none of the when conditions are met. Finally, the end keyword closes the case statement. A simple case statement is useful when you're checking a single column against a list of exact values. For example, to provide a more descriptive full name for departments, you can select the employee_name and department, then use case to specify that when the department is IT, the full _name is technology, for HR it's human resources, and so on, with an other default for any unlisted departments. A searched case statement offers more flexibility as it allows you to evaluate different conditions that aren't necessarily based on a single column's direct value. Here, for product_name and price, you can categorize products into budget, mid-range, or premium based on price ranges. For instance, defining budget for prices under 100, mid-range for prices between 100 and 500, and premium for prices over 500. You can also embed a case statement directly within a where clause to apply complex filtering logic. For example, to select employees based on varying salary thresholds depending on their department, you could use case to specify that if the department is sales, the salary must be over $50,000, but if it's IT, the salary must be over $60,000, and otherwise over $40,000. When combined with aggregation functions, case statements enable powerful conditional counting or summing. For each department, you can count total_employees, and then use case to conditionally count high_earners, those with salary over $50,000. You can also use case to calculate average salaries separately for male and female employees, effectively creating conditional aggregations within a single query. The case statement is excellent for data transformation, converting raw data into more meaningful categories. For customers, you can transform their age into age_group categories like minor, adult, or senior. Similarly, you can define customer_tier, VIP, premium, regular, based on total_purchases, making the data more understandable and actionable. For even more intricate logic, you can use nested case statements, where one case statement is embedded within another. This allows for multi-level conditional evaluations. For employees, if their department is IT, an inner case then further defines their job_title based on years_experience into senior developer, developer, or junior developer. A separate inner case would apply for the sales department and a general default for others. Finally, case statements are frequently used in update queries to apply conditional changes to data. For instance, to calculate bonus amounts for employees based on their performance_rating, you would set the bonus column using a case statement. This allows you to assign different bonus percentages to the salary depending on whether the performance_rating is excellent, good, average, or a default of 0 for other ratings, streamlining complex update logic. The exists operator in SQL is used to test for the existence of any rows returned by a subquery. Its primary purpose is to efficiently check if a subquery produces one or more rows, without actually retrieving the data from that subquery. It returns true if the subquery returns any rows, and false if it returns no rows. The basic syntax involves selecting data from your main table 1 where the exists operator is applied. Inside the exists clause, you place a subquery, typically select one for efficiency, from table 2 with a condition that links it back to the main query. A common application of exists is to find records in a main table that have a corresponding entry in another table. For example, to retrieve customers who have placed orders, you would select from the customers table where an order exists in the orders table for that specific customer_ID. Conversely, the not exists operator is used to find records that do not have a corresponding entry in another table. To identify customers who have never placed any orders, you would select from the customers table where an order not exists in the orders table for their customer_ID. You can include multiple conditions within the subquery of an exists clause for more specific checks. For instance, to find employees who have managed projects specifically within the IT department, you would check for the existence of projects where the manager_ID matches the employee_ID and the department of the project is IT. While exists and can sometimes achieve similar results, exists is often more performant, especially with large subquery results, because it stops processing as soon as it finds the first match. For example, to find customers who placed orders on or after a specific date, you could use exists to check for relevant orders, or in with a subquery to list the customer_IDs. Exists can be more efficient as it doesn't need to build the full list of IDs. The exists operator is particularly effective with correlated subqueries, where the inner query depends on the outer query for each row. To find products with an above-average price within their respective categories, you would use exists with a subquery that calculates the average price for the current product's category and checks if the current product's price is greater than that average. You can combine multiple exists conditions using an or to check for complex relationships. For example, to retrieve customers who have both placed orders and submitted reviews, you would include two separate exists clauses, one to check for the existence of orders and another to check for the existence of reviews for that customer_ID. Using exists with date conditions is common for finding recent activities. To find employees who have had performance reviews within the last year, You would check for the existence of a record in the performance_reviews table for that employee_ID where the review_date is on or after 1 year ago from the current_date. The exists operator is a handy tool for detecting duplicate records. To find duplicate email addresses in the customers table, you can select from the customers table and use exists with a subquery that looks for another customer record with the same email address but a different and greater customer ID. This ensures you only pick up one instance of each duplicate pair. And that's a wrap for this long video covering intermediate topics for SQL. Trying to get all of these at once might be overwhelming, so divide them into parts and then start. Thanks for watching this video. And if you watched this far, then please give it a like, share it with your friends, and do subscribe to the channel. See you in the next one. Till then, happy learning.